Okay. The discussion that we are going to have in this tutorial is that we're going to talk about some numerical methods that it's going to be a building block and the crucial methodologies when we just deal with the Bayes estimators there. But before we just talk about that, as you probably may have noticed, the discussion that we're going to have is going to be, as you see from this picture, which is the area of the Monte Carlo and Monaco. Probably you should have guessed that the thing that we're just going to talk about is going to be Monte Carlo simulation, or with the thing that we're just going to talk right now is going to be the Monte Carlo numerical methods. That's going to be a very building blocks and the crucial thing when we are just going to talk about the Bayes estimators, because in those estimators, knowing to how just have the numerical values of those, I should say, a multi-dimensionals integrals, is crucial to know how to just use the Monte Carlo methods then. Okay. Then before we start, I'm just going to just go over some very basic things that we have learned before. We have seen that for very, I should say, a limited number of the integrals, which you probably should have seen that even from the high school, that for example, from the advanced placement calculus, that for some basic integrals, for example, like the one that I'm just going to write, for example, like if our single variable is going to be the x, and if it has the components of the n, which n is not equal to 0, with respect to the variations of the f of f with the x, we learned that from the high school that the result of this integration is infinite, I should say, integration is x to the power n plus 1 and n plus 1. And you notice that also from this result, we have to just make sure that n is not going to be something which is, I should say, equals to minus 1. Because if x is equal to minus 1, there is a different method to find the result of this integration. And we just call that always, because that's an infinite integrals. Infinite integrals, we have to just add a constant c at the end of, I should say, our integration. This family of the integration, which is a very limited class of analytical integrals, they are so easy to deal with that, because analytically we can just start from the integrand, which is, as you will see, that the integrand which we have here is x to the power n, to just get to, let's say, for example, a definite number as the result of the integral. But however, there are some, for example, functions that when we just want to find the analytical value of, I should say, the integrals, for example, imagine if you have a function, that function is a function of a multi, I should say, variable, I should say, of, let's say, the random variables of x1, x2, x3, and goes all the way to the xn. And you will see that we have the x1, the x2, and it goes all the way to the dxn. You see that for these integrals, analytically, solving these integrals is not going to be an easy task, and they become intractable if you just want to find the exact values of these integrals. Then the thing that we just do is that we just come here for this type of the integrals, specifically the ones that they are, I should say, for example, like the functions that we have inside the integrand is going to be, I should say, a multivariate function. Then these integrals, they should not be analytically tractable. Then what's going to be the solution? What's going to be the strategy that when we just want to deal with these type of the integrals? There are many different variety of approaches when you just want to just look into the numerical methods. When you just want to deal with these type of the integrals. One of these methods that we are just going to talk about is going to be, we are not going to talk about much about these type of methods, because these are the things that there has been more extensive works, books, and lectures on them. Then I refer you to some of the ones on, let's say you can just find it in any elementary textbooks on the numerical methods. Then we talk about, for example, we have deterministic. We have some deterministic approaches. What do we mean? For example, imagine that we have a function. This is going to be the y-axis, this is going to be the x-axis, the random variables. And we have the function which is plotted somewhere like that. Now, the thing that we just want to do, we want to find to come, for example, from the a to b. Find the value of the integral, if we may just call that, for example, the integral of f of x, d of x from a to b. And as you will see, the f of x is going to be the function which is highlighted by, I should say, this color, which is almost red. The thing that we do is that we find a trapezoid. Then we say that, for example, we can divide, for example, these areas as, for example, that's what we call that the trapezoid. Then we say that, for example, for each one, we are going to come, for example, to just find a summation. It becomes, for example, the summation of, let's say, for example, xi minus xi minus 1 times f of, let's say, for example, xi that we have, for example, somewhere in between, and the I goes from, for example, let's say, for example, from 1 goes, we prefer to just have it goes to the infinity. Then we assume that as the number of the, I should say, the trapezoid that we have between these 2 points and in B, it gets larger and larger. We can have an approximate which is going to be closer to the true value of the area under, I should say, this curve, which is going to be a deterministic method to just find the numerical value and approximations for those type of the functions which they are analytically intractable. However, for the thing that is going to be the focus for this tutorial, we are going to talk about a second type of methods for numerical analysis, which is going to be, I should say, non-deterministic. The second type is going to be, let's say, the type that we call the non-deterministic. Non-deterministic, or simply we call them stochastic. Because as stochastics, I should say, methods. Because at every time you run the method, you may have some different values then. Because as you will see on the discussion that I'm just going to have in just a couple of seconds, you get to understand why do we say that these methods, they are just going to be named as indeterministic or non-deterministic methods in numerical methods of the values of integrals. Okay, let's start with one typical, I should say, structures of these type of integrals, which is essentially the method of the Monte Carlo numerical analysis. Imagine that I have an integral but before I we just go with directly with the integral, let's go to have our very basic Cartesian plane, which it represents, for example, the x on the x-axis and the transformation of the x with respect to the function of the f on, let's say, on the y-axis. We say that for the functions that we have designed here, which is, let's say, which is going to be the, for example, for the random variable x, we call that a variable because we are not going to fix, for example, x to any value, for example, like 12. We are not going to just set it, for example, at that value. That's why we call it random variable. And we call that random. The reason for that is that because we do not give a very specific direction in order to localize and identify the value of the x. For example, we do not say that, for example, you just walk. For example, need 2 units towards the right, then take 1 unit towards up, and you just find the points there. The x is going to be located there. Then you can just randomly just walk anywhere you desire to just find a value of the x. And that's the reason we just call x as a random variable. Imagine that for the x that we have, it is going to still be a random variable. However, this random variable, imagine that, for example, it's going to be defined by a distribution. There is a probability for the x at every point to just find that point in. That's how we say that our random variable has been, I should say, defined by a probability distribution that we can just find the probability for each, I should say, for each localized spots of that point that we are interested in. And that's why I say that, for example, if I assume that the x is going to be my random variable, this randomness also is defined by a probability distribution. I call that a distribution for the x. For example, it can be a normal distribution that we should have, for example, the mean of it, and I should say the dispersion from, I should say, the central point of the distribution. It can be any type of the distribution. It can be gamma. It can be any type of distribution. Then imagine that we have these points that we say that, okay, we have p of x, which is going to be our probability distribution, which defines the random variable x. And at the same time, imagine that we are just going to also design another function, which we call that, for example, any type of the functions, which we call that, for example, it's going to be f of the x. For the f of the x, we just come here to say that, for example, what's going to happen if I just want to, for example, that's the thing which normally happens with the Bayes estimators, that we say that what happens if I just come here and say, if I have p of the x, which I have also the functions f of the x times d of the x, and now we are interested to find the value of this integral. And that's going to be the topic that we're just going to talk about, and we see that with this type of the methods, that we have normally a probability distribution defined, I should say, the random variables, and that's, we have a functions f of the x, and we say that, okay, we just want to just come here and find the expected value of, let's say, of the function, which is going to be our functions of f of x, with respect to the probability distribution of the p. That's what we call that the expected value of, let's say, the function f of x. However, this random variable is designed by a distribution which we just call that, for example, p. That's the structure and the backbone of our analysis. Now, the thing is that in Monte Carlo, we do not want to just come here to analytically solve this integral. For example, imagine that you have a distribution. This distribution can be anything. This distribution, as you will see that, I should say, on the next tutorials, sometimes the distribution are so easy to just work with them, to just find the numerical value of the integral. However, for some of the other, I should say, distributions like the p of x, it makes the integration, I should say, analytically intractable. Then that's why we just come here to just use one of the rules, and we say that if, imagine that if I just call this integral, if I just call this integral I, and I say that I is going to be defined by this integral, then I said that the I can be approximated by the average, I should say, this is the sigma sign which I have, my f of x, evaluated, I should say, at each random value which I extract from random distributions which I have at each point. I can just start from 1, goes to n. And you say that, I just say that, for example, it can goes to the n. And as you will see here, n can be any number. It can be any random number. You can just have a sample which consists of 2. You can have a sample which n is going to be 10, n can be 100, or n can be a big number, literally big number as 1 million. Then in that scenario, we say that, okay, the integral which we have, then it's going to be approximated to this value, however, with respect to 1 over n. Which, the thing which you will see that here, it reminds you of something which we have talked about that, and I call that In, which it says that this is going to be the average value of the function f of x at each point which we have taken out from the random, I should say, distributions that we had, but we had our sample population, for example, going from 1 to n. This is essentially the thing that you see that this is one of the results of one of the most important results in statistics, that we call that this is going to be the law of large numbers. We call that this is going to be the law of large numbers, and we see that the integral, which was intractable analytically, can be approximated just simply by the average of the functions evaluated at each point of our distribution. However, let's go back to, I should say, I'll just go to the next slide, because we have to talk about, I should say, also the concept, I should say, of the concept of the convergence, to see that if we have a convergence for the sums that we are just going to have, and how it can be close to the value that we expect to be the exact and the true value of the integrals that we had in here, that we talk about this one here. We said that there is, we can come to with this scenario. We said that if I have, imagine that, for example, the integral, I just called the integral which I had on the previous page, I just called the integral the I. We call that, if I can say that, if I can just define the absolute value of the exact value of the integral and its estimation, which is going to be derived from the n sample points which we got from that distribution. If I can just come with this scenario that I can just define the difference of the exact value and the approximated value, and it's good to just write that here. I call that, for example, the true value, which sometimes we call that also the exact value. And also I just call this one as an approximate value. We can come here to show that if we have number of, I should say, number of the samples that we had, which it was n, we can say that as n goes to infinity, then the limit of this value tends to go to 0. Which essentially, as an interpretation that we can just have, is that we say that if we have large number of, I should say, the trials that we're going to have from our simulations, for example, n is not going to be a small number. Let's say, for example, we have 2 random variables from our the distribution. We are not going to have 100. We're talking about a large number of the samples. For example, about 1 million, 100 million, and it can even goes to infinity. Then we can expect that the result of this difference, the limit at the infinity for all sample sizes, goes to 0, which you can say that it can denote the fact that the integral, it's a very interesting conclusion. Then as a result, it can be, let's say, for example, let me just write a bare shape of the integral. Then it can be said that, for example, the integral of the functions that we had times the probability distribution that is attached to the functions with respect to the variations of the f of x, then you can say that this integral can be equal to the summation, I should say, of 1 over n of the sigma of f of xi, I should say, there are random variables from the population, I should say, the distribution of the p. They can be from 1 to n. However, they can be equal as long as they have this very, I should say, crucial restriction that the n should go to infinity. Then as a result, that's going to hold true. And although it's going to be, I should say, the scope of the tutorials that we're going to have, you can also just go to different text. You see that the speed and the rate that this integral is going to converge to this value, which is the average value of the functions evaluated at any points of the distribution. We call that the rate of convergence. Is essentially proportional to 1 over square root of the n. Then you see that as long as n goes to infinity, you have a higher rate of the convergence, and the function gets closer and closer to the true value and the exact value of the integral that we defined and that we defined it here. And essentially, that's what we call that the Monte Carlo estimation. And we talked about the convergence rate of this method, which is going to be the proportional to the inverse of the square root of, the number of the samples which you have decided to just pick up and choose and extract from the population, from the distribution density that you have designed it here. Then essentially, as you saw, that's how we define the Monte Carlo estimation in the numerical methods as an undeterministic or indeterministic methods of evaluating an integral which is not analytically tractable. Then at the sample sizes that it goes to infinity, we can assume that the true value of the integral is going to be equal to the average of the function evaluated at every single point at that density that we have defined for our integrand. On the next tutorial also, we're just going to talk about some other variations of this method, which is going to be crucial for our analysis. And as a very final point, you saw that when we talk about the n as the number of the trials, sometimes we can think of the n as a number of the trials, and as you will see that on our regression analysis within the Bayesian context, sometimes we have a huge number of the iterations in our samples, because we assume that if we just take more number of the iterations, then the Monte Carlo, convergence is going to happen fast, and that's going to converge actually to the true value of the integral that we are looking for. Then before I finish, I just want you please look at these concepts here, especially the concepts of the convergence that we talked about, and also especially with the number of the n that we talked about that, and this method that is going to be the Monte Carlo estimation. We're just going to go back to these concepts more and more again, and it's going to help you a lot when we just go for advanced sessions then. I see you in the next tutorials with more interesting stuff.